Hey everybody, I'm Molly McKinney with NASA 360 coming to you live from NASA's Langley Research Center. As you can see, we are in the historic hangar here at Langley Research Center, and we are covering one of my favorite competitions of the year. This is the second year in a row that we've covered the Rascal Mars Ice Challenge. And though it may not look like the surface of Mars behind me, we have teams that have gathered from across the country to compete in this really exciting challenge as we simulate the surface of Mars. And let me give you a quick little tour of the pit area really quick. Teams are using harvesting systems to try and collect ice and eventually water from large ice deposits like we found on the subsurface of Mars. And let's make it as difficult as possible for our camera operator as we have him walk up these stairs. But this is going to be a really nice vantage point to introduce you to this challenge and what teams are tasked with doing. Most teams have used a design that's similar to this one, where you can see this auger drilling system. Teams have to drill through this subterranean simulated Martian soil. Are we on your way? We can move if we are. And underneath this soil are these large ice deposits like we found on the subsurface of Mars. Teams are tasked with the very difficult problem of extracting ice and eventually water. Once teams are able to get their water, that funnels through different filtration systems to get a clean sample, and then look at that nice NASA logo placement there. It's collected into this bucket. Goal of the challenge is to get as much water as you can in the bucket, and then teams win. What's really interesting about these designs is teams have really differentiated in how they've decided to tackle this challenge. Some teams extract water right from this soil collection bin. Other teams actually turn the ice into a gas vapor form first, and then they condense it back into a liquid form, which is really interesting. It's probably something I wouldn't have thought to do. So it's really fun to compare all the different technologies and see how university students are tackling this challenge. But the perfect person for me to speak to about this challenge, to give you a really nice overview, is Rick Davis from NASA. He's a NASA expert. I love talking to you every time I get the opportunity, Rick. And look at this. It's a great view of all the different schools that are competing here for this challenge. So, Rick, give us an overview of what this challenge is and why it's important.
So I work with the Mars Exploration Program, and Mars is actually, when you get pictures from Curiosity, it's kind of misleading sometimes because it makes it look like you're in Arizona. And if you really wanted an analogy, it's like being on top of Mount Everest or K2 times 1,000, because the pressure at Mars is like being at 110,000 feet on this planet. The temperature drops 120 degrees at night, and and we're just finding out all these really cool things like constantly. So for about 10 years ago, we began to realize we weren't even looking for it, that there's buried frozen oceans and glaciers at Mars. And so that's like really new information. And so a lot of our technology development had not been even focused on the fact that there's oceans there. And so this is really a great opportunity right now, because students can actually make a contribution to figuring out how you go into the dirt, or regolith as we call it at Mars, get down into the ice and actually pull up water so that you can actually support human beings being there. And so it is like cutting brand new ground, and NASA's done some work as of other entities, but it's so new that these guys actually, it's not just a STEM type event. It's actually, they're helping pave the way. And that's one of the reasons we were very excited to increase the number of teams this year so that we can get more ideas. So it's really a very exciting time.
This isn't just a nice to have little experiment or little competition. This is a real challenge that NASA is trying to solve internally.
Yes, exactly. And the thing is that I don't mean to say Mars is a bit like the internet was 25 years ago, in the sense that back then you just needed people who who were really excited about it, who were really turned on to try to figure out how to crack these problems and challenges, who understood that we is more important than I, and had humility to learn all the things that needed to be learned. And you didn't even really back then need to have a college degree, and I'm not advocating for that. But what I am saying is that when you have those other attributes and you're really excited about these things, you will help us figure out, how to do this together. And, we need ideas. Mars is hard. You need ideas not just from NASA or within the United States. You need them from all over the planet to actually go crack this. And if we can get those ideas, and that includes university students on design teams like this, we will figure out how to do this.
This challenge centers around water collection, which is important for hydration and personal hygiene. But what are some of the other, maybe out-of-the-box solutions that water could help us with in terms of deep space exploration?
So actually, the real thing we need it for immediately is not even obvious, because you actually said all the things that I would normally think of. But the fact of the matter is that when we send a crew to Mars, we're going to pre-position their rocket to come home on. And to reduce costs and to make this affordable, we're actually going to fuel it up with resources from Mars. And so,
pardon these drilling noises. We really are in a working hangar, and the competition is underway.
So the big thing is you can get oxygen from the air or the atmosphere, but the big one we need is hydrogen molecules to generate methane. And methane is the fuel. And the access to this water is the big thing we need right now so that the crew can come home.
So challenges like this really are crucial for us to solve these problems now to make deep space exploration possible.
You need to be operating on multiple fronts. Challenges like this is a critical tool for actually helping generate ideas that we have not thought of. And I'll go one step further. So when you're coming up through schools nowadays, they're doing things differently. They're doing CubeSats they didn't do when I came through. They're using computers and softwares in ways that we never did. We need those new ideas to actually come in here and help distill the right answers.
As a NASA expert who is actively working on the Mars exploration team, what technologies have you seen here that really surprised you or felt out of the box to you?
So last year, it's hard because you're...
Like choosing your favorite child.
Yeah, so last year, well, let me start with last year. You know, when you were drilling down, you don't really know what the dirt layer is, right? And then you've got to get down into the ice. That is not a simple thing, because here on this planet, when you're doing drilling, you're doing wet drilling. You'll see them using water. This is dry drilling. They got to get down to the ice. And last year we had one case where they actually solved the problem. They're our one team that actually generated water last year. This year we already got 3 teams that are generating water, which is fantastic. But when they got down there, they overheated it, and the whole thing collapsed on them because we're learning how to do those things. And
this is new.
It's new. And so that's one example of a lesson that we learned here, that a number of us learned, that I think we'll be able to carry forward. And so I fully expect more this year.
That's really exciting. I'm very excited to talk to some of these teams. You're welcome to come with me if you want to. So I'm going to head over and talk to West Virginia, and I'm really curious to hear the differences between these drilling systems. Teams had to submit a design for how they would tackle this challenge on Mars, and then they had to submit these actual designs for the prototype that they have to modify to test here on Earth. So is this a good time? I don't mean to pull you away. I know you're actually drilling.
The drilling cycle is automated, so we're just waiting on a preferred depth to be reached right now.
You have ear protection in too. It must get pretty loud.
It does. Our lab was louder than this hangar, so it was louder. Good, thank you.
So this is wonderful for you.
Yeah, this is.
So walk me through your prototype design and how it differentiates from some of the other ones we might see today.
Midas 2 only uses one probe to go down to ram into the regolith and collect water. You can see the other probes, they might use 2 or 3 different systems to go down into the regolith and collect water. But we only use a single probe to reduce the chance of any errors with the regolith falling down when moving different probes. And also the one all-in-one probe system works well for our Rodwell system we're trying to form in the ice.
Can we hop up here while we talk about it? I guess it'll be a little louder. So walk me through. You have your one probe that you're removing the soil with, and then how are you collecting ice or water? What's the next step in your process?
We are actually not removing the soil. The soil is like moving apart. The probe acts like a spear as it goes in. It doesn't.
See, this is so different than some of the other teams. Why did you choose that approach?
To keep the soil contained so it doesn't collapse, and an all-in-one probe is more simple. Like, we like to keep things. Midas 2 is a very simple system, so
less room for error. I like it in theory, right? Murphy's Law. So walk me through the process once you've removed the soil.
Once a certain depth is reached, we'll blast out heat. We'll blast heat at a different heating rate, and it'll create a Rodwell, which is a form, which is a shape of that forms in the ice. And once the rod wells form, the ice will melt into vapor, and
Then you condense it back into liquid form?
we don't condense it because we only get 127 milliliters of steam, but we do get 3.3 liters of water per hour. So we use a pump to pump the water once the heating cycle is finished. So it's a lot of waiting and
Hoping everything goes smoothly. Well, I hope it goes smoothly for you today. I appreciate your time. I'll let you get back to work. I know that you're working right now. Thank you. It was nice meeting you. I cannot multitask and have my phone at the same time, so I'm going to do a couple call-outs really quick to Mary, Eileen, Abel, Rudy, Marcus, Anne, and Jeremy. Thanks for joining us, you all. And so our next team that we're going to talk to is right over here. Hey, are you Emmy? Nice to meet you. I'm Molly. Do you mind it? Can I pull you away really quick? Is that all right? Yep. I know everybody's working today, so talking to me may not be your most favorite thing to do. Can you walk me through your system?
Absolutely.
I have to hold this microphone really close to you because it's very loud in here.
Gotcha. All right, so our system starts with our auger right here. And so we go down and we drill a hole to just above the ice. And so what we found actually today, which is really great, is that the hole is really nice and clear. So we just get the ice surface. And so then we've got our extractor, which is in the hole right now. And so that goes down. We've got a heated tip on it. And the heated tip actually articulates, so it can bend around in a full circle. And so at the bottom of that tip, we have a tube. And so as it melts the water, it pumps up, and then it goes into our filtration chamber, and that's powered by electroflocculation. So basically our particles clump together, they fall to the bottom of the chamber, and we have clear water. And that's kind of...
That's brilliant. I've never heard of a team doing that before.
Yeah, the electroflocculation is a really cool feature. Yeah, that's up there.
If you guys can see this right here, that's what we're talking about, is this really unique filtration method. Can you explain it one more time?
So it works the best with clay because clay has ionized particles. And so basically we have an anode and a cathode that create a magnetic field. And so then the particles clump together in the field, and then they're heavier, and so they just fall down better.
That's wonderful. And a clean sample is important in this challenge.
Yeah, it is. We've actually done really well with that. If you look in like our nut bag where we have our collected sediment, there's not a lot in there. So we just have turbid water, which is okay. So it's going really well.
Are you happy with your water yield thus far?
We are super happy with our water yield. It's been going really well for us, which is nice.
Is that concerning then, because you're waiting for something to happen? It's going too well. It makes you uncomfortable?
A little bit. We actually just had a small crisis in which one of our tension lines that articulate the bottom of the extractor broke. But, we all ran in and we fixed it real quick. It was like a 15-minute job, and we're back to working. So
now tomorrow when you're hands off, will you be able to do things like that? Okay, so today you're able to hop in, touch things manually, but tomorrow it's not autonomous. You can still remotely control it, but you have to be hands off. So that'll pose a new set of challenges. That's great. Well, for those of you that are just now joining us, we're here at the Rascal Mars Ice Challenge. Teams have been tasked with the difficult challenge of extracting water from ice, and we're using these simulated Martian soil or regolith for teams to be able to drill through and collect these water samples. And obviously the most water that teams can get, the better it is, and the better chance that they'll win. So the challenge itself consists of two main components. The first is design, and the second is demonstrating. This is what you're seeing today is the demonstration part. So teams had to design an ice and water harvesting system for using on the surface of Mars. And then they had to modify that design so they could actually test it here on Earth. So that's what you're seeing today is these teams using these harvesting systems and seeing how they work on Earth conditions. Obviously, before we send something to Mars, we'd like to really understand how it works. And so opportunities like this are things that NASA really does here on our planet to test our different experiments and our instruments before we send them into deep space. The atmosphere and gravitational pull on Mars is very different from Earth. So building a system for Mars that we test on Earth is not an easy task, and that's part of what makes the Mars Ice Challenge so challenging. Each team brings a different idea to the table. all of this diversity of ideas really helps us expand our collective understanding and gets them ready for day 2, which is the really hard day of this challenge. Today is day 1. Teams are allowed to physically work on and touch their systems, but any water they collect is worth fewer points. On day 2, which is tomorrow, these Mars ice drilling systems have to work on their own with no human input. So water harvested today is worth, or tomorrow is worth 3 times the points. So we have another team that I would love to talk to if it's a good time. It's always difficult on days like this because there's so much important work happening. I hate to be invasive, but let's see if Vu has a second. Vu, can I pull you away for a second? I know as programmer, you're integral to this team. So Vu, tell me a little bit about your role in this challenge and for your team.
So my role in this challenge is to basically control the robot and to implement the programming and all of the electronics. And that's essentially what I've been part of this team for.
So you really are the brain of this machine, of this drilling, harvesting.
All the ideas that we've implemented were from everyone that was on this team. So like Jake Rosenthal's idea was for the filtration, with the evaporations and the chamber itself, using condenser to get the water out. Minzin Du, he's not here right now, but his idea was to have a compartmentalized auger to separate the dirt and ice while we're drilling. So all of these ideas that we've had are implemented by all team members. So I wouldn't say I'm the brains.
And this is why you work on a great team. I'm sure they really appreciate you and not taking credit. So you're controlling, for the most part, remotely, and tomorrow you definitely will be controlling remotely. How difficult is that task?
It's not too difficult. So how we're controlling this robot is using Arduinos and using our interfaces on the computer. So all we have to do is just know what's going to happen, and since we have our data logging right next to our control computer, we just look at what's going on and we can infer what's down inside the test bed itself.
From a programming standpoint, what has been the most difficult part of this challenge for you?
Learning how to program.
Were you a programmer before?
No. So I've had like some experience in C++ and Python, but I haven't had this much experience programming a whole robot by itself.
Would you do this again?
I'd probably do it again. It was a fun time.
What are your hopes for achieving today, since this is day 1 and you have a second day tomorrow?
So one of my hopes is to drill into the dirt and try to get to the ice layer. So then tomorrow we can potentially start getting the ice itself.
And hopefully some water.
And hopefully some water, because tomorrow is a lot of points.
Well, may the force be with you. I hope it goes well. I'm sure it will. And you've got an awesome team behind you, so that's really wonderful. So if you're just not joining us, this is the Rascal Mars Ice Challenge. Teams are trying to harvest water from these ice deposits that we've buried under a simulated Martian regolith or Martian soil. And this is the pit area, so you can take a quick little tour and look at all of the different teams, all of the different systems. They've traveled here from universities all over the country to compete in this challenge. There were dozens of teams that tried to compete today, and these are the top 10 that made the cut. Some cool facts: the hangar that we're actually standing in at NASA's Langley Research Center is really important historically. It's where Apollo astronauts practiced the lunar landing, and in fact, there's still some equipment up in the rafters of the hangar here that were used for practicing that landing. NASA actually plans to have robotic landers acting as scouts on the surface of the moon in 2022, which will enhance scientific and strategic exploration of the moon, hopefully leading to eventual human exploration of Mars, which is what this challenge is all about. Another cool fact is that this is the 60th anniversary of NASA this year. Congratulations. And next year will be the 50th anniversary of John Glenn and Buzz Aldrin's first steps on the moon. What's really cool about this challenge is that it focuses on NASA's mission with in situ resource utilization. Part of exploring the solar system is living off the land and whatever available resources we have wherever we go. It's going to be really difficult for us to explore deep space if we don't have access to some of the resources that we're used to. So future astronauts will need to be able to collect space-based resources and turn them into breathable air, rocket propellants, building materials, and of course water for drinking and hygiene and plant growth. So if you guys want to take a step over here, we're going to talk to this team, which is what's so exciting about challenges like this. You ready? Yeah. Oh, I'm interrupting lunch too. I'm so sorry. Everything's so we're talking a little bit about space-based resources and why challenges like this are so important. So were you intrigued by the water collection aspect of this challenge when you first heard about it?
Yeah, definitely. We're all grad students actually, and most of us work on in situ resource utilization like this for Mars or something similar. Really? Yeah, all of our research is kind of involved with getting humans to Mars. And so working on resources like this is really important for that.
I explained it a little bit that for us to be able to go into deep space, we can't be dependent on Earth-based resources. We have to use space-based resources. But for someone who's not familiar with in situ resource utilization, can you give an overview of what it is?
Yeah, for sure. So basically, in order to send humans to Mars, it costs a lot to send all the consumables that they'll need on Mars, like food, water, oxygen, things like that.
Because the ISS gets deliveries of this cargo today.
Yeah, exactly. So if we can make that on Mars using resources on Mars, it saves on the order of hundreds of millions or maybe even billions of dollars, depending on what we're making there. And Mars has resources we can use, like water, so that's why this is so important.
So walk me through your design. It looks like you are using an auger, so it is a drilling system.
Yeah, so basically we have a dual auger, and what we kind of like about our design, and we think it sets us apart from others, is you can't quite see it right now, but we have an outer auger, which is here, and there's actually some flutes down in the dirt right now, and an inner auger, which is protruding out of the top. And if you notice, the flutes are in opposite directions. So what this means is we can basically drill down through the dirt in one direction with the outer auger, and then we can flip the motor direction, and it actually drills down into the ice with the inner auger and leaves the outer auger behind. And that creates sort of a shell to preserve all the ice and not allow any dirt to get in there to contaminate it. So it's a dual auger system, and it eventually deposits all the ice into this oven right here.
And so that's actually how you're creating water.
Yeah, that's how we're creating water. We melt the ice in here, and then just in case some dirt does get through, which might happen, we have a series of filters here and valves that allow us to filter out any dirt before we collect it in the collection bin.
I like these shirts. I didn't even notice those.
Yeah.
Does this show your team name on the back?
Our team patch on the back.
And where are you all from?
We're from MIT in Boston.
And the grad school program at MIT. So was it difficult to travel to a competition like this and re-erect a drilling system? Usually they all work fine and your home campus, and then you bring them here and there's something that doesn't want to play nicely.
No, so I got to fly here, but these two had to drive the thing down from Boston, which
They got the short straws, huh?
yeah, it was a pretty big trip. But they did a good job of packaging it up. It only took us 2 or 3 hours to unpack it and reassemble it, so it wasn't too bad.
Wow. And so what goals are you hoping to achieve today versus tomorrow?
Yeah, so today we're basically testing out our system with this dirt and ice. The dirt is a little bit different than what we tested with back home, and so we're trying to get a sense of how it works with our outer auger. It's a lot wetter than we had expected, so we're trying some different things, different speeds of translation and also spinning in order to see how the motor can handle this wet dirt, and then hopefully tomorrow we'll actually be able to extract a lot of the ice.
Wow. Well, I hope that you'll be able to extract it too. That's interesting that the regolith is wetter. Surprise from the test that you did?
Yeah, it's just we made a mock-up of this whole system, and our dirt was just a little bit drier is all, so it acts a little bit differently.
There's always something,
Yeah.
you know, it keeps it exciting. Wouldn't be as fun. Well, thank you for your time. I'll let you get back to it. If you're just now joining us, this is NASA 360's live coverage, live, so you never know what I might say or you never know what might happen, of the Rascal Mars Ice Challenge. We have teams that have gathered here from universities all across the country, and they're competing today to try and extract water from ice deposits that we've simulated hidden underneath some Martian regolith or simulated Martian soil. What's really neat about challenges like this is each team brings a different idea to the table. All those diversity of ideas helps expand our collective understanding as well as NASA's collective understanding, because these are real challenges that NASA is trying to solve today. These aren't just made up things that we're hoping to challenge students with. NASA scientists are challenged with them, right? And so on day one, teams are allowed to physically work on and touch their systems, but any water they collect is worth fewer points. And then on day two, these Mars ice drilling systems have to work on their own with no human involvement, so you can't actually touch the systems tomorrow. And those will be worth 3 times the points. Most teams today you'll see are using an auger system to drill through the simulated Martian regolith, and it really depends on the team from there as to which ones are harvesting ice and melting it in the chambers. Some are doing that right in the soil container, and others are letting the ice condense to a gas form, and then they're converting it back to water. So it's really been fun to see creatively all of the different approaches that teams are using. Obviously, these discoveries and the technological advancements we're able to see here are really helping us not only understand ourselves and understand our own technology, but they're helping us push the envelope of what's possible in the universe and deep space exploration. And Chris, you're probably the perfect person to talk to about why challenges like this are so important, not just for NASA, but for business industry and for our country and for the world.
Absolutely. I mean, if we're going to do human exploration, whether it's to the moon, whether it's to Mars, pretty much any destination, we're going to need water, and we're going to need a lot of it. So we're going to use it eventually to keep the crew alive. We're going to use it in order to provide the propellant to bring them home. We're going to use it even in more advanced ways. We could make plastics from it someday. So for all of these reasons, it's really critical we understand how we can acquire water at another destination in space to make these missions possible.
What do you think is the most, challenging challenge about this challenge?
I mean, a lot of it is. Probably the autonomous operations is going to be tough. When we did this last year, that tripped up a lot of teams, and it'll probably be tough here. It'll be tough when we as NASA try and do it at another destination, because we're going to be working, especially at Mars, with a multi-minute delay between us sending a command and the system operating. So in that time, we've got to rely on these systems to work and do all of this very difficult work in a hard environment all by themselves, essentially. So that's the one that really scares me.
Probably validly so, yeah. If you're just not joining us, this is our NASA 360 coverage of the Rascal Mars Ice Challenge. And one of the things that seems difficult to me for these teams is they not only had to design a system that would work under Martian conditions, but then they had to modify that design to work here on Earth. What are some of the complications that teams would run into with an Earth-based model if they tried to use it on Mars?
So the environment at Earth versus the environment at Mars is pretty dramatically different. The temperature at Mars is significantly colder, but even more important is the atmospheric pressure there is about 1/100th of that which you're going to find on Earth. So because of that, when the ice is exposed to the surface, there's a very real risk it will immediately turn into a vapor and go away before we can capture it. Now, some teams have actually talked about using that to their advantage in their system design, but all of them have to keep in mind how different that Martian environment is in order to not only have a system that works here for the competition, but more importantly, a system that we could someday take to Mars.
We touched on this a little bit earlier, but in situ resource utilization is a big mission for NASA right now as we hope to push the envelope into deep space exploration. Can you describe what space-based resources are and why they are important for us to be independent on Earth?
Absolutely. So the single biggest challenge we've run into with rocketry pretty much from the start is it takes a lot of energy to get anything off Earth to another planet or to the moon. And so because of that, it's very expensive for every single pound we want to send elsewhere in the solar system. So if we can get the things we're going to need at the destination, if we can mine water on the moon or on Mars, if we can use the regolith and the dirt there in order to build structures to live in, if we can take advantage of the atmosphere there to slow us down as we're arriving and to provide oxygen to breathe there, that saves mass that we need to send and thus makes it a lot easier in order to tackle those missions. And it'll be even more important when we start really trying to build a more permanent presence for humans out in space, where we really need to try and get them more independent from the supplies they get from Earth.
So these challenges like this are really tasking the challenges that NASA is running into and facing. And what I love the most about these opportunities is these are students that could technically be competing against each other, but you don't see that. You see a camaraderie between them. Everyone seems to be working together towards this common goal, and I just think that's so neat.
It's really amazing to see. I mean, yesterday one of the members of the team went out and actually made a Home Depot run essentially for all of the other teams in order to bring supplies to them as they needed. So they've really been working together a lot, not treating it as some cutthroat competition that they're desperate to win. Instead, they're really, they all each do want to win, but they're also working together, and it's been very collegial, and it always is really nice to see that from the student teams.
I love that. And it really helps because NASA's discoveries in aeronautics and space exploration, science and technology are transforming our understanding of ourselves and our planet and our solar system and our universe, you know?
Absolutely. You know, everything we're doing here with NASA, both today and more broadly across the agency, is to better our understanding of the universe, and it's also to help humans be able to go out and explore these new destinations. And what we're doing here today is just one important but small piece of that bigger picture. Again, whether we're going to try and send humans to the moon, whether we're going to send them to Mars, all of this kind of fits into that bigger picture of what the agency's goals are.
I love that. And I think it's so great because this really is the next generation. I mean, some of the folks that you see right here on the floor today, they are the researchers of tomorrow. And so it's going to be really amazing to see what they accomplish as they make the next giant leaps for humankind. I wish that we had more time to show you today. We will be back at 2 p.m. Eastern today, so you can take a look and see if teams have extracted any more water, but unfortunately we're out of time for this show. On behalf of NASA 360, I'm Molly McKinney, and if you'd like to find out more about what your space agency is doing, feel free to follow us. We're at nasa.gov/NASA360, and we have Facebook and Twitter and a new Snapchat account today, so we'd love to show you all the things that NASA's doing. So stay tuned. We'll see you next time. Bye.